Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to Technogenial. Our today's topic is medium transmission line. As you all know that we already studied short transmission line. In the last lecture, I told you that there are three types of model in the transmission line. One is short, second one is medium, and third one is long transmission line. Today we will discuss the medium transmission line. So here we are in the short transmission line. We have seen that we ignore C component because we said that the value of XC is very large, and as it is connected in parallel, so there would be no current travel in the C portion, and so it can be ignored. But in the medium transmission line, the value of C is not so much large, so we cannot ignore the C component in the medium transmission line. So if the C component is added in the transmission line, then you can see that the overall circuit would be uh, in two different formation. It can be either in T formation or in pi formation. In the T formation, as shown in the figure, we will divide the resistance and the inductance component into half. Half side is on the right side and half side is on the left side. While the C is in the mid portion, we have C and G, the conductance. So we can represent in a impedance or R plus JXL into Z, and we can represent capacitance into Y. So admittance. Now the simpler formation of the circuit is Z by 2, in the left side, Z by 2 in the right side, and in between the two Z by 2 we have Y. So this formation is known as T formation. As you see that it appears like T in the form of T. We have Y in the middle, and we have Z by 2 and Z by 2 in the left and the right side. While there is another composition which is known as pi composition. In pi composition, we divide the capacitance into half, one in the left side and one in the right side. However, we consider R plus JXL as a single quantity. Now R plus JXL is represented by Z, while C by 2 is represented by Y by 2 and Y by 2. Now the capacitance component is divided into half, while the impedance component is in a single part. While in T component we convert impedance component into half and admittance component in a single part. So these are the two models in this. While modeling medium transmission line, we will study these two models. Now if you see, if we calculate ABCD parameters of the medium transmission line, then for the parameter we consider the transmission line as a black box. It has two inputs and two output. The input is sending end voltage and sending end current, while the output is receiving end current and receiving end voltage. So if we want to find the output, we need an equation in terms of in terms of the parameters of the transmission line with the combination of the output parameter. So the equation would be input is equal to ABCD parameter into output. So input is sending end voltage, sending end current, and the output is receiving end voltage, receiving end current multiplied by ABCD parameter. If we expand this equation, we would have voltage, sending end voltage is equal to A into receiving end voltage plus B into receiving end current, while sending end current is equal to C into receiving end voltage plus D into receiving end current. Now we start with the T model. In the T model, as you already know, I already told you that we divide the impedance portion into half. So we have R by 2, XL by 2, Similarly, r by 2 and xl by 2. So in between these two we have jxc. From the sending side we can say that we have voltage Vs divided by under root 3, and from the receiving side we have R divided by under root 3. So these are the four different parameters of the transmission line. Now if we want to find the voltage in the midpoint, this midpoint, the voltage in the midpoint is the receiving end voltage. Receiving end voltage plus the voltage drop across the this impedance is equal to the voltage A at this point. So the receiving end voltage plus IR into Z by 2, because the combination of R plus JXL is Z by 2. So we have V mid is equal to VR divided by under root 3 plus IR Z by 2, and the shunt current, shunt current which is the current which is passing in the capacitance area. So the shunt current is the if you see that it is the mid voltage, the voltage which we calculate over here, into the into y, that means impedance, admittance. So we have V mid into y. So V mid, the value of V mid is this one, VR divided by under root 3 plus IR Z by 2 into y. So from this equation we can calculate ISH. Now if we want to develop the equation of the current, then it is the sending, when this sending and current goes in the straight line. Now it is divided into two portions. One is ISH and the second one is IR. So the IS is equal to IR plus ISH, and the equation for ISH is this one. So it would be VR divided by under root 3 y plus IR into 1 plus ZY divided by divided by 2. ZY by 2 is from this one, and we took IR common. So this IR and this IR will make it 1 plus ZY divided by 2. So we have two equations. One is for the IS and the second one is for the VR. Now for the second one we will calculate VR. Now the VS, if you see this equation, we have the VS is equal to the voltage of the midpoint plus IS Z by 2. This voltage, the voltage drop across this point and the voltage drop across this point is equal to Vs. Now the V mid, the value of V mid is this one, VR divided by under root 3 plus IR into Z by 2. So this is the value of the V mid plus IS, the value of IS is this one. Now the value of IS into Z by 2. So from this equation we calculate Vs divided by 2. This is the sending end voltage equation and this is the sending end current. Now if we put these two equations in this equation, then sending end voltage, receiving end voltage into ABCD into VRIR. So the coefficient of VR would be A and the coefficient of IR would be B in sending end voltage. And in the sending end current, the coefficient of VR is C and the coefficient of IR is D. Now from these equations we can find that the component of VR, the component of VR is A, the component of IR is B, this one is B, the component of VR in this equation is C, so it is Y, and component of IR in this equation, it is 1 plus ZY over 2. So this is the whole equation. We have A, B, C and D. In order to verify this equation, with the formula is the A should be equal to D and AD minus BC is equal to 1. If these two equations are satisfied, that means the parameter which we calculate ABCD are exactly according to our requirement, and the model our calculation is okay and correct. Similarly, for the pi model, we divide admittance into half. We have y by 2, and we consider r plus jxl as a single unit. So in this equation, if you see that the current is dividing the series current is divided into shunt at the sending end and the shunt current at the receiving end. So the sending end current is equal to the sum of sending shunt at the sending end current, shunt current at the receiving end, and the receiving IR. So these three currents need to be calculated. So for the ISHR at the receiving end, we can say that the voltage across these value divided by the impedance or multiplied by the admitter. So it is YR divided by under 3 into Y times Y by 2. Similarly, for this one, this current is the voltage across this one. This is Vs divided by under root 3 into Y by 2. So the receiving end shunt current is this one, and the sending end shunt current is this one. So now we want to develop the equation for the sending end voltage. So the sending end voltage is from this figure. You see that voltage across the receiving end, this one, the voltage across the receiving end, the voltage drop across RXL is the sending end voltage. So the sending end voltage is receiving end voltage plus Z into IR plus ISHR. So the current would be IR, the current would be this one, this current, and this current is basically combination of IR, this one, this current, and this current, IR plus ISHR. So if we put the value of ISHR, which we calculate over here, then the overall equation would be this one. Similarly, if we want to calculate the sending end current, it is IR plus ISHR plus ISH. So IR is this one, IR plus VR over 2. That means when we put the value of SHR, this is the SHR, VR divided by under 3 into Y by 2. So this is ISHR, and ISHS is Vs divided by under 3 Y by 2. So this is the overall equation. But we won't need the equation of Vs and Is in terms of VR and IR. But in this equation we have sending end voltage. We need to convert this equation in just two parameter in which we have VR and IR. So we have to put the value of Vs over here. So the value of Vs is VR by the under root 3 1 plus Z y by 2 plus IR into Z. So if we put the value of Vs over here, then we can get Is. Now we have the two values. Vs is this one and Is is this one. So in the Vs, the component of VR is A, the component of IR is B. So component of VR is 1 plus Zy by 2, and the component of IR is B, and it is Z. For the C, the component of VR in this equation is C. It is Y into 1 plus Zy by 4, and similarly the component of IR in this equation is D. So we have this one. So in order to verify that these parameters which we calculate is accurate, we have to check that A should be equal to D. So if you see that the value of A is similar to D, similarly if we multiply A into D minus B into C, the result would be 1. If these two equations satisfy, that means the parameter which we calculate are accurate. So for the pi model, we have seen that the ABCD matrices is this one. If we put the value of ABCD in this equation, it is VSIS into ABCD into a VRIR. Similarly, if we want to calculate VRIR, then we will take the inverse of this matrices into VSIS. Similarly, the power loss in medium transmission line is I square R for the active power. It is I square R for the reactive power. There are two reactive powers. One is due to the inductance and second one is due to the capacitance. For the inductance, it is QL, and QL is equal to I square into XL. While QC is V square into B, and B is the admittance. So these are the two values. In order to calculate the voltage regulation, then we have the sending end voltage minus the receiving end voltage divided by receiving end voltage, but we have divided by A, and A is the magnitude of the line constant A. So A is a constant value which we need to calculate. So this is the equation of the voltage regulation. Now now this is this is an example. A three-phase 138 kV transmission line is connected in 49 megawatt load at 0.85 lagging power factor. The line constant of 52 mile long line, or RZ, is equal to this one and Y is equal to this one. Using nominal T circuit representation, calculate the following: ABCD, sending end voltage, sending end current, sending end power factor, efficiency. Now initially we have the voltage over here, and the voltage in the is 138 kV. Now we need to calculate VR, and so for the VR we divide the voltage by under root 3. Now we have the VR, line to neutral VR. The voltage which is given is line to line or phase to phase voltage. Now we will calculate line to neutral voltage. So and for this one, as there is no angle, so we can consider it as 0-degree angle. So the receiving end current would be IR is equal to the power divided by the voltage into under root 3 into power factor. So the power is 49 megawatt, and this one, the power is 49 megawatt divided by the voltage into 0.85 into under root 3. So overall current is this one, the receiving end current. And if you calculate the angle, we can take this inverse of this thing, and it is minus 31.8. Now for the ABCD parameter. For A, if you see from this equation, we have A, B, C, D parameters. These from this equation, and we will put the values and we will get the ABC. So we have 1 plus 1 by 2 into Y plus Y into Z. So we have Y, we have Z. So if we put the value of Y and Z, we can find A. Similarly, we can find B, we can find C, and we can find D. Now the equation is sending end voltage, sending end current into ABCD into receiving end voltage into receiving end current. So the sending end voltage is calculated from this mathematical equation. If we expand this equation, we will find that the first quantity multiplied by this one and second quantity multiplied by this one. So we will have the sending end voltage. Similarly, we can find the sending end current, and the sending end current is this one. We will multiply this row with this column. We will get the sending end current. Now we have the sending end current and the sending end voltage. We can find we can find the efficiency, and similarly we can find the angle. So the angle would be the we have two angles, 10.4 and 11.3. So if we add them, we have 21.7, and if we take cos phi, it is 0.929. Similarly, the efficiency is output over input. We have the output is the receiving end power divided by input is the sending end power. So if we divide it, the efficiency of the system is 94.27. Now now in the previous example, we calculate everything by using T model, and now in this example we will calculate everything in the pi model. So for the pi model, where we have a little bit different equation, we have A. So from A we can now the equation of the A is 1 plus 1 by 2 z yz. Similarly, we can find B, C and D. For by finding these all values, the overall matrices would be like this one. And from this matrices we can find the sending end voltage, we can find the sending end current, and we can find theta. Similarly, for the we can find the efficiency. If you see that from these two numericals, although the equations are little bit different, but the results are similar. If you see that this one, the power factor is 0.929 and the efficiency is 94.27. The for this it is 0.927, almost near to the previous result, is similarly 94.16 efficiency. So the results are almost same, but the equations are different. Thank you. Jazakallah. Stay blessed. Allah Hafiz.